Cool. So, yeah, welcome to week three. Did you guys feel the earthquake yesterday or last night a little bit? Cool. Yeah, it's definitely interesting experience. But anyways, so announcements. So if you're unable to make it to discussion or lecture, please let us know in with a private post on Ed. If you can't make it to discussion, you could also check it off in office hours. Um, so yeah. For the attendance and check off grade sheet, we're still working on it, but hopefully we'll get that to you guys sometime soon. So discussion two was released last Friday, and it's due this Friday before discussion, and discussion three will be released this Friday. Any questions with logistics? Good. Awesome. So this is the agenda for today. We're going to quickly recap about Swift UI. And then we're going to talk about a feature called closures. And then we're going to talk about how we could get data flowing into your UI. And that kind of pertains to using something called for each. How do we display a list of data and how we can have sections within those lists. And then we're going to wrap up the discussion about view identity. So I in the last lecture, I didn't have time to kind of finish the whole demo, but I posted the code on the ed post, so you can feel free to kind of copy and paste in Xcode and see how it goes. How many of you guys would like me to do like a video demo of the SwiftUI from last lecture? Would that be helpful or yes? Okay, I'll probably get that up then. Um, cool. So just to recap, a view defines a piece of UI. So every view that you see in your code, that's a piece of UI. And every UI you see on your device, that's a SwiftUI view. And so, like we mentioned, Apple provides us a lot of fundamental or rudimentary views for us to use. And you can think of these like Lego bricks, right? Lego gives us a discrete set of tools or bricks for us to build more complex Lego projects, right? And so these are just some of the built-in SwiftUI views that Apple gives us. All right, you can think of them Legos bricks, and then you can create them to create more complex views. Now, how do we create those complex views? We use something called composition. So we use composition with, for example, stacks. So we talked about three different types of stacks. We talked about an H stack. An H stack basically aligns its subviews horizontally, right? And then we talked about a V stack, which is basically, again, a container that aligns its subviews vertically. And then we also talked about Z stack, which is aligning all of its subviews on the Z axis, sort of like Photoshop layers. Now, how do we actually modify a view's behaviors and properties? Well, that's something called view modifiers. So, like its name, it modifies the view. So here in this example, we have a text, right? And it just says hello. And then to modify its text color, we use something called foreground style, this view modifier, and we give it a color blue. And if we want to bold or we want to specify the font weight, we could use this bold view modifier. So we could chain these view modifiers to create more or customize our views. And each time you do add a view modifier, what happens is that it will create a new view. So when I apply its foreground style, it'll create a new view. And when I apply bold, it will create a new view on top of the new view that's being created above. So it just kind of chains downwards. So the order matters for some circumstances. For example, let's say imagine this was padding. So we use the padding view modifier to add some padding around the view itself. And then we add, for example, dot background, and we give it a color, a background color. So what will happen is that here, when this padding, the color is applied to the padding and the text. So you can think of like, the whole like this area is all with a background color. Now, if these were switched, so the background color is here and the padding is here, well, the background color would be applied here, like the boundaries of hello, but the padding outside around it will not have that background color. So the order for some circumstances of how you apply view modifiers is critical. And we talked about how SwiftUI is a declarative UI, in which basically says you tell SwiftUI what you want, and as the data changes, as we'll see later, the whole view re-updates and re-renders. So again, this is the demo that I didn't have time to make it through last lecture. You can take a look at the code here and put in Xcode, play around with it. I'll probably create a video to kind of go through step by step if that helps. Uh, what happened there? Um, Yikes. I think my computer just I think Keynote just there you go. Okay. And so here we also have, I mentioned also a app called SF Symbols that you could get from the Apple developer website. And it's basically Apple crafted icons that you can use right within your apps. And all of the icons are crafted with a sense of consistency and familiarity. So it kind of evokes kind of the same iconography of the iOS symbols that Apple uses. And it's customizable. So you can customize the font weights, different colors of it. There's also different animations. So some symbols, you can add like a wiggle effect, kind of like scale effects. So yeah, if you haven't downloaded it, please download it so you could use it within your apps. All right, so that's a quick recap of SwiftUI. Now let's talk about something called closures. Okay, this is kind of it's not a Swift particular feature, but it's sort of unique, or the syntax is kind of sort of unique to Swift. So closures are self-contained blocks of functionality that could be passed around and used within your code. For those who have taken 61A, these are basically lambdas. And one of the unique properties of closures is that they could capture and store references to any variables or constants outside or within the context in which they're defined. And we call this kind of closing over those constants variables. And again, these are all just kind of jargon, but we could take a look at what closing over means. So there's kind of three types of different closures. One of them are the functions that we've been writing, or global functions, and they don't really kind of capture any outside values outside. So when the function finishes running, it doesn't retain values outside of its environment. The second type is called nested functions, in which you can have a function within a function. And those functions can have a name and can capture values or retain variables in its surrounding outside the lifetime of the function call. And third are closure expressions, which are unnamed closures written in a lightweight syntax that can capture or retain values from their surrounding context. And this is basically like lambdas if you've done 61A. So let's take a look at what capturing means, right? So capturing means you retain a reference to constants and variables from the surrounding context, even when the original scope of the function that defined them no longer exists. So here in this function, you can see that we have, it's called make incrementer, and it accepts a parameter called amount, which is of type integer, and it returns something, right? You can see this arrow sign that means it returns something. Well, what does it return? Well, interesting. It's not, now we have, it's not a single integer, it's not a string, but it actually returns a function. So what does this mean? Well, it returns a function that accepts no arguments, okay? And this function returns an integer. Again, it's a bit trippy. So let's take a look at what inside this function, what does it do? So we have this variable called running total, which is initialized to 0 from the beginning. And we have this nested function. And again, remember from last slide, a nested function is also a closure. And this nested function returns an integer. It's called an incrementer. And what it does is that it takes the value here that we passed in from the outer function, right? And we increment running total by that amount. and then return the resulting new updated value of running total. And then here in the make incrementer function, we're returning incrementer. So incrementer rate is a function, right, that accepts no arguments and it returns an integer. So let's take a look. Yeah, an incrementer is a closure. And what I mean by capturing a reference, it retains the value of amount, right? Here, even when make incrementer finishes running. So that's what I mean by capturing. It's able to like retain the value of amounts from its surrounding context, even after when make incrementer is gone, right? It finishes. Because if you imagine what make incrementer does, right? It basically runs running total. Here's the function, it returns it, and that's all it does, right? But within here, it's able to capture it. It's able to retain the amount, the value of amounts, right? That we could use later on. So again, this is the same function make incrementer. Let's create a new variable, a constant variable called increment by 10, and then we're going to assign it to whatever make incrementer returns, and we're passing 10 into amount. So what this does is that increment by 10, right? It's not an integer. What is it? It's a function. It's a function that returns an integer. So when we call this function, right, we increment by 10, what happens is that it's going to return 10. Well, why? Well, because we passed in 10 into here, right? And it's going to increment running total by 10. It's going to print that out. So now it's 10. If I call this again, it's going to be 20. So this running total now is 10, and then we increment running total by 10 again. So that's 20, and then so forth. So as you can see, this incrementer, this nested function is able to kind of retain the value that was declared or passed in here. But if you create a new incrementer, so if you call make incrementer somewhere else and assign it to new variable and you call that function, that has a separate running total instance. Okay. Again, it's a bit trippy. It's sort of like if you watch the movie Inception, where it's like a dream within a dream within a dream, and then you're kind of getting out of the dreams back out. It's sort of weird, but hopefully that kind of analogy helps. One of a really kind of common closure usage is with sorted. So sorted, the syntax that we use sorted is the third case, like it's sort of like a lambda in Python. It's written in a really briefed and focused syntax. So sorted takes in an argument that accepts a closure, basically a function. Remember, again, a closure is basically a special function. Accepts a closure that takes in two arguments of the same type of array contents. So, and it returns a Boolean for ordering. So if the function returns true, that means the first value should appear before the second value, and if it's false, it's the other way around. So for example, if we're sorting on an array of strings, the closure type that it accepts is a function with two arguments with those strings and returns an integer. So let's take a look at this code. So we have this an array of strings called names. And here we have this function called backward, right? And this is sort of the function that we know and love and that we're used to, right? Accepts two arguments, S1, S2, both are strings because we're operating on an array of strings, and it returns a Boolean, right? True or false value. So what I want to do is that I want to order or generate a new array of strings where the elements themselves are ordered lexicographically reversed. So I want I want Ewa here, Daniela, Chris, Barry, and Alex. So they're just in the alphabet, they're just ordered reverse. So here we're basically saying S1 is greater than S2. So what that means is that if I pass in two strings here, what I'm saying is that I want you to sort this, I want you to sort these two elements where the first one should have a lexicographically greater value than the second one. So for example, if this was the letter A, if this was letter B, I want to sort these guys so that B comes first. So what we do is that we can basically get this new array right, by calling sorted on names. Again, sorted returns a new array of strings, and we basically pass in this function. So what this does is that it's going to sort names by this rule that we gave in, which is backward. And so, yeah. So here's backward again. Now we can actually make this, we kind of make it so that it's more simple. So we could rewrite this function. Again, remember, a closure is a function. We could write this using this kind of closure syntax where we have these, again, brackets here, but now we have our parameters within these parentheses, and then arrow, the return type of the function, and then we have this in keyword. This in keyword just basically separates the parameter and return type from the actual function implementation. So we could rewrite backward into something that looks like this. Again, same thing, but we're now kind of embedding the function within sorted. So again, this this curly bracket, this function takes in two arguments, S1, S2, returns a Boolean, and this in keyword separates the parameters here, the return type, from the function, the actual function itself. Again, these are two exact same things, but we're kind of nesting our backward function into the argument itself using closure. All right. We can actually do even better. So Swift, okay, we can make this into a single line, so they're not separate lines. So now we have a single line. We can even do better. And Swift is sort of smart, right? It knows that we're calling sorted on an array of strings, so it expects that S1, S2 are strings themselves. So it can infer that S1, S2 are strings. So we can just drop the type notation. Now we could do even better. We can actually drop the return keyword because, well, the closure here, this function expects us to return a Boolean. So it knows that we're returning this. This is a Boolean. This is a true or false value, right? So we can drop that return since that's inferred. Now we could do even better. We could rewrite it using this weird syntax. So we could say this $0 is greater than $1. What does that mean? Well, $0 is in reference to the first parameter. The second one, $1, is in reference to the second parameter. So basically what we're saying is that, all right, we have an array of strings. I want to get a new array of strings sorted by this condition where basically the first or the element, if I have two pair, if I have a pair, I want to sort this pair where the I want the greater lexicographically ordered one first before the second one. So yeah, and so we call these $0, $1 shorthand argument names, where again the first $0 is the first argument of the closure, and the second one is the $1 is the second one. If you have more, if the function has more, arguments, then it'll be $2, $3, and so forth, right? But this kind of syntax is just kind of, it just makes sense, right? I want to sort this array of strings called names where I want, if I'm given a pairing, I want it to sort it where the lexicographically greater one is first, then the second, right? Does this make sense, sort of? Cool. So that's closures. Next, let's talk about data flow. So here we have a view. Again, I didn't really talk about buttons, but this is how you actually do a button in SwiftUI. So it takes a closure. Actually, it takes two closures. Here, right, it takes in one closure. It takes in a function, basically. And here it takes another closure. And I won't go in the syntax right now, but again, this is a closure. This is called a trailing closure syntax. So where this button is a function, I swear it's like a function. It takes in two parameters, action and content. Now, if the last parameter is a closure, we could basically drop that parameter name and then bring it out outside the parentheses and using this kind of like syntax. So again, this is a closure. And this is where we actually show the content of the button. So here's the content of the button, and here's what happens when we tap on a button. Like this will run, right? So what I want to do is that when I tap on this tap me button, I want to increment num taps by 1. However, we have a problem, right? When you try to do this in Xcode, you're going to get this error called left side of mutating operator isn't mutable. Self is immutable. My goodness, what does this mean? All right, this is very kind of archaic. This doesn't make any sense. Well, as we talked about, structs are value types. And what it means is that once you have created a struct, right, that variable, you can't change it anymore. Or in a sense, our structs are kind of immutable. Like once you created it, you can't really change it. So inside of this struct, right, this view, we have this kind of variable called num tabs. And again, once it's created, the properties within the structs can't change. So you have to do something else than this, right? So regular struct properties cannot be mutated within their own structs. And this is just by design. This is just the behavior of structs. Classes you can, but structs you can't. So how do we mutate these properties, right? And we can't create a class. Okay, so all views in SwiftUI are structs because they're lightweight. And so because of the lightweightness of structs, SwiftUI can basically update our views as many times as it wants without having a big performance impact. So what we do is that we declare a source of truth. So what I mean by source of truth, that's like the original location of the data itself. So what we do is that we add this syntax called at state, and in an at state, every single time you see an at, that's a property wrapper. A property wrapper wraps around a property and adds some additional functionality to it. Well, what is this additional functionality when I add at state to a property? Well, now the variable is not the basically the data management of this variable is now not under the struct, but SwiftUI will come in and it will take care of the memory management of numtabs. So numtabs is now handled by SwiftUI. Now, what does that do? Well, whenever numtabs changes, SwiftUI will announce that, hey, numtabs changes, and whoever uses numtabs re-update yourself to reflect the new value of numtabs. Okay, does that make sense? Again, an at state states or creates a source of truth, the actual location of the data, where SwiftUI manages that data, and then whenever that data changes, SwiftUI will basically say, "Hey, if anyone using numtabs, update yourself appropriately." And it's really efficient, and it will only re-render the views that are using dependencies. So it only re-render views that are using numtabs. So in this case, it won't update this button because the actual button content does not depend on numtabs. Now let's change it. So now we're actually creating a dependency to numtabs. So in this button, right, we have tap me, exclamation mark. And remember, this is string interpolation. What this does is it embeds the value of this variable within the string. So right now it's 0. So we have this tap me, exclamation mark 0. Now, what happens when I tap on this button? Well, the value of numtabs changes, and SwiftUI will say, hey, are there any views that are using numtabs? Or in other words, are there any views that form a dependency to numtabs? In this case, our button does, because the content of this button depends on numtabs, right? So since there exists a dependency, what happens is that SwiftUI will tell this button to re-update itself using this new updated value of numtabs. So now we see tap me 1. Right, if I tap this one more time, right, what happens? Numtabs, that becomes 2, and the button will re-render itself, so now it would show tap me 2. Does this make sense? Okay, again, at state. Whenever you see an at state, that is the original location of the data. Now, why do I'm stressing this original location of data or source of truth? Well, our views can get quite complex, right? We can have views within views within views and within views. Now, let's say I want to, okay, we built our button and it's a really amazing button. And I want to use this button throughout my app. Now, what I don't want to do is to copy and paste the button code around like everywhere. What you should do, right, as we saw in last lecture at the very end, was to put it in a new custom view. So what I've done is I've refactored the code. Refactor just means reorganizing our code so that we have created a new custom view called incrementable button. And again, this is the same UI that we have earlier with this button, numtaps increment by one, and shows tap me with the numtaps value. And then we're using it in a parent view called content view. And then we're basically creating our incrementable button here. And then we're passing numtaps. Again, the source of truth is in content view. We're passing it to numtaps. This is how we can get numtaps into incremental button so that we can use it here and here. Okay. But like I mentioned before, an at state declares a source of truth. The issue here is that we have two at states, all right? So again, our goal is to have a single numtaps, a one source of truth. Where should that source of truth lie? That should lie in the parent view, right? We should have the source of truth in content view. And what we want to do is that we want to sync up these numtaps here to numtaps here, right? So that's our goal. However, since within here we have an at state, it actually initializes a new place in memory. So now we have two numtaps that SwiftUI manages, one in content view and one in incrementable button. So when I'm actually tapping here, so, it only changes the one in incremental button, but not the one in content view. So there's an issue here, right? So again, we have two numtaps now, but we just want to have one, which is in the content view, in the parent view. So how do we reconcile this discrepancy, this problem? We introduce another property wrapper called at binding. What at binding does is that it allows a subview to read and write from and to a source of truth in its parent view. What does that mean? Well, now instead of at state, I use at binding on this parameter. And the second change is that I now pass in not the value of numtaps, but I pass in a binding. So every at state has an inherent binding inside of it. So we basically use this $sign to say, I want the binding version of this numtaps. So at the call site, we pre-prend the argument with a $sign to pass in a binding rather than the actual value. If we just did numtaps, that's actually just 0. But we want a binding. And we annotate the property in the child view with an at binding. So in incrementable button, we can read the value of content views numtaps here, and we can write back to content views numtaps via here. So what this does is that we have a single source of truth. We have a single variable called numtaps that lives in the content view. We pass a binding into incremental button where incremental button can read the value of numtaps here, and also it can write back to it to numtaps. So when I tap on when I tap on this button, what happens is that it changes the value of numtaps here. Okay, because again, there's a source of truth, a single place where the data lives. It's here. So it now is 1. And since here it depends on numtaps, it will basically re-render itself to show the data value. Does this make sense? Okay, cool. Let's take a look at another view. This is called text field, which is a built-in view in SwiftUI. And it's basically a text field. So if you ever look at an app, like a login page where it asks you to enter your username or email, it's probably using a text field. So I want to create a custom text field with a header. So what I've done here is that I've created a custom view that takes in binding, and it takes in a static parameter called header, which is string. And then I'll align these guys so that they're vertically aligned, right? With a VStack, where the header is above the text field. Now, the text field API requires a binding here. So it requires, for example, like a placeholder, and it also requires a binding to the text field. So if you look at the implementation of, or sorry, the declaration of a text field, it requires a property, or sorry, parameter called text, and you give it a binding string. So how does this all work together, right? So our source of truth, where is our, so okay, when the user types in a text field, we want to capture that data, right? Where does that data actually live? It lives right here in content view. That's the source of truth. Now we pipe it down into our header text field via this binding, where header text field can read header. Sorry, it doesn't need to read. Yeah, okay, we pass in the header here. It gets header, but this text field binding, we pass it down to text field. So internally, SwiftUI and Apple's code, right? When the user types in the text field can write back to the source of truth of this place. So when the user is typing, right, where do we get the text? It actually changes here. Does that make sense? So again, it's like layers within layers, right? We're basically passing a binding into header text field. We pass that binding down into text field, and then again, internally, Apple's code, when you type in a text field, it writes back to this place. It will write back, and then we get our values here. Okay. So again, it's kind of weird, but this sort of makes sense a little bit. Okay, cool. Any questions? Cool. All right, so that's data flow. Let's talk about how we can display or structure our data. So in other languages, you might see, like for example, JavaScript or TypeScript, there is something called for each. And what that does is that basically loops, it's sort of like a for loop. Basically, you basically take each element in a sequence and you basically act on it. So wouldn't it be nice? A lot of times when working with data, we have like a list of data, right? Wouldn't it be nice if we could create views based on some data, like an array of strings, and we show a list of like people? So here we have in our content view, we have a VStack. Okay, basically, like, and we have a text, 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 text. Now, these are all static, right? If some new students come in, we can't change it, right? These are just like set in stone. Now, what if we want our data to be dynamic, right? So we can actually specify an array here, just a list of student names, and then we can loop on each of these students using this for each. So for each students, and then here we basically, again, this looks like this is a closure. Okay. So basically, again, we get here, we get the name of each student, and then what do we return? Return a text. So for each student, we return a text with a student name. Now, each one of the requirements of for each is that each of these elements within this for each must be an identifiable. Identifiable is a protocol. And again, for those who have taken 61B, that's the interface in Java. In simpler terms, a protocol is like a law. Okay, it's a law. A protocol has a set of rules, a set of like functions or a set of variable names that whoever wants to be that protocol needs to implement those rules. One of the rules in identifiable is something called if you want to be in an identifiable, or if you want to conform to identifiable, you must implement the ID property. Um, if not, you can provide a key path. So, for example, let's say you have a struct or a class, and you're iterating on those instances. And maybe you have a student struct, and on that student, you have like student ID, or you have like some unique identifier. And then here in this ID property, you could do backslash or whatever, yeah, backslash dot ID or student ID. Um, and the reason why for each requires each of its elements to be identifiable or be able to uniquely identify each element is because of animations. So when things come and go, or when things delete or get inserted, SwiftUI knows how to animate that automatically. So this is the identifier protocol that I was mentioning. So again, this is what, for example, if you have a student struct, if the student struct were to implement, or sorry, conform to identifiable, again, we can think of protocols as like laws. If you want to be identifiable, you have to implement this ID property. And here we assign it to something called UUID. Um, and a UUID is basically an object that universally identifies unique values in objects. For those who have taken CS 161, computer security, you probably know about UUIDs. It's just basically a pseudo randomly generated like string, basically. It's just like basically a string of just random values. So here, since we conform student to identifiable, when we create an array of students, we can just drop the ID parameter here because for each is able to identify each student via its ID property. So what it does is that it basically corresponds each text to its ID. And then when things come and go or changes, SwiftUI is able to animate that automatically. Now, when I talk about, again, the key path, again, the second option is to provide a key path. So we could drop the conformance to identifiable, but you need to provide some value for each to keep track, or basically, or for each to associate each view to some unique value. And in this case, let's say that student ID property in your student struct is always unique. You could say, hey, I want you to identify each view via its student ID property. So when you hear key path, that's like a property, okay? And we use the syntax slash dot student ID as the key path of the student ID property in the student struct. The third way is backslash dot self. For those who have taken 61B, you might have heard hashable or hash values. So for values that are hashable, you can supply slash dot self for the ID property. For those who have not taken 61B, what is hashable? Hashable basically says that a value or a struct, for example, it can give you a unique value for those values. So in a sense, for example, let's say, okay, Swift primitive types like integer strings are all hashable by default. Let's say you have our student struct that we have earlier. If student ID is 0, for example, okay, if we create a new student object with student ID 0 and name, for example, like Oski, and if I create a new student instance with the same values, student ID 0 and name Oski, when I compute the hash value, so there's a hash function that you take these two values, you put it inside, it will generate hash values. Those hash values are the same. Okay, so it's just basically you getting like a sequence of bytes or strings, whatever, that for the same instance or the same object, it gets you return or you get out the same hash value. So if things are hashable, we could use slash.self, means the whole object. So basically, Swift computes the hash value of the entire object and uses that as an identifier. Why? Well, again, if two objects are the same, have the same values, when you compute the hash value of these two objects, they're the same thing. Okay. Yeah. Okay. So for example, here in this example, since strings are hashable by default, we can use id slash.self to get to identify or associate each text to each string's hash value. Okay, so let's talk about how we can display a list of data. So a list is simply a container that presents rows of data arranged in a single column, or you can also have the ability to edit. The syntax is very simple. List, the sequence that you want to iterate upon, you get back each of the elements in a sequence, and you return some view. We can create multi-dimensional lists, so you can think of these as 2D array, or like it's like 2D array. So we can use sections to group subgroups of our data. So let's say here we have a list that allows us to scroll. Each section has, this is the content of each section. It's a for each. We generate all of the views based on our favorite fruits. And then within the header, we can put some custom view here as we want. And here we have same thing for fruits that are bad. Cool. So that's for each, lists, and section. Finally, let's talk about view identity. So this is quite important. So the question with view identity is, are these two circles the same or different, right? And that's a question of view identity. So same views, if they're the same views, we expect them to have the same identities. So if the views are the same, we expect the red one to move. So let's say I want a blue circle here, right? And we have the red one earlier. If those views are the same, we expect that red circle to move down and transition into the blue color. Same views, same identities. If they're different views, they have different identities. So again, the same thing, I want a blue circle here in the result. But if they're different, the behavior of the red circle going down or becoming that blue circle is different. Instead, it just transitions because they're different views, right? Now, there's two types of identities I want to mention. One is called explicit, and one is called structural. Explicit identity is defined by custom or data-driven IDs, like we talked about with for each. Again, why do we need an ID? It's for SwiftUI to associate the view to some unique identifier so that it can do like animations. So the ID parameter is a form of explicit identity because we're explicitly saying, hey, this view is associated to this ID. If the data changes, SwiftUI is able to generate the appropriate animations automatically. For example, deletions, insertions, and modifications. What does that look like? Well, if you ever see some apps, right? When you click on them, the things jump down, they slide down, right? Well, that's because SwiftUI is able to basically identify each of these views by its IDs and animate them properly. And whenever you like swipe to delete, the thing goes whoosh, and then the whole thing just like goes up, right? Well, that's because of the ID property. The second type of identity is something called structural identity. So we're not specifying a view associated with an ID. We're associating the view how it's positioned in the view hierarchy. So here we have an example where this user variable is an optional, and it's an optional like user struct. And we're using this technique, remember from last lecture, called optional binding to get the value if it has a value, right? And assign it to this variable user. And then if it does exist, we show this logged in view. Else we show this authentication view. So for example, we want you to log in into the app. So SwiftUI is able to identify the differentiation between logged in view and authentication view because of this else if else branch, right? So it treats logged in view and authentication view as two separate different views. So here we have an example where we have the circle, right? It's filled with the color red. If we want, okay, we have the state property called show red, right? If it's true, we show red. Else, we show blue. Again, this is a hypo. It should be color.blue or just dot blue. I forgot to put a period in front. Anyways, so if we change show red to be false, what happens is now is that it transitions to a new view to the blue circle by fading in and out. Okay. Because of the structural identity, because of this if else, they're two separate views. Now, how do we make it into it's the same view? So now, instead of the if else branches, we just have one circle, and we conditionalize this fill color based on if show red is true or false. You might see this syntax from other languages. This is called the ternary operator. So what this means is that we have a condition in the front. If it's true, we do the thing here after the question mark. If it's false, we do the thing after the colon. So if show red is true, we show color, we fill the circle with the color dot red. If it's false, we fill the circle with color dot blue. So now, since they're the same views, when show red is now false, oh, sorry. If it's false, it does not fade in and out anymore. It just basically changes the color into blue. It's the same view, right? So it preserves the view and just changes its fill color. So just to recap, the difference between explicit and structural identity. Again, the main question I want to answer is that if you have two views from two different screen states, are those views the same or are they different? If they're the same views, they have the same identities, SwiftUI applies the new state to that view. If they're different views, they're different identities, SwiftUI will transition them independently, right? Fade in and out. And if they're different views, those views are destroyed and recreated. So explicit is defined by custom or data-driven identifiers like the ID parameter in for each. Implicit, or you call it structural, the same thing, implicit or structural, are defined by the view type and it's positioned in the view hierarchy like an if-else statement. Prefer using the second approach with the ternary operator. And the reason is because it's more performant. SwiftUI doesn't need to destroy and recreate views. All right, so just to quickly recap, we talked about closures, which are basically self-contained blocks of functionality that can be passed around and used within your code and can capture variables or data from its surrounding context. And these are basically lambdas in Python. And you could use them with built-in functions like map. Map allows you to transform the elements in a sequence based on some function. Filter allows you to filter on some collection based on some condition and sort and etc. At state and at binding, at state declares the source of truth, the original location of the data, of mutable data in SwiftUI views, and an at binding works in conjunction with an at state to create a two-way read and write connection to a source of truth and a parent from its child view. For each allows us to create and derive views based on data. Lists allow us to display a list of data, a scrollable list of data, and supports editing and selection. We can group together similar data together using sections. We talked about view identity of whether if two different views in if two views in different screen states are the same thing. There's two of them. There's explicit, which are basically defined using custom or IDs, and structural or implicit, which are defined by how it's positioned in the view hierarchy, like using an if else. All right, so we have time